Previously, we learned how to find zeros of polynomial functions. Now, we're going to learn how to create polynomial functions in standard form given the zeros. You can also use them given a graph. Let's start out with a polynomial function in standard form that has the zeros 5, 4, and -2. First, in intercept form, this would be x minus 5, x minus 4, and x times x plus 2, or quantity x minus 5 times the quantity x minus 4 times the quantity x plus 2. This is because each one of these zeros substituted into the equation for the input would produce an output of 0. So 5 minus 5, that gives 0, multiplied by these values is 0, for example. We've seen this before. Now, in order to write it in standard form, then we have to multiply the binomials together. I suggest first taking one of them and then multiply the result of the two products of these binomials by this binomial. Take each term and distribute to each of the additional terms. Finally, combine the like terms. And here we have a cubic function, x cubed minus 7x squared plus 2x plus 40, that has the zeros 5, 4, and -2. Let's go ahead and graph this one. So x cubed minus 7x squared plus 2x plus 40 gives the graph. Let's adjust the window slightly. So that all the zeros will be seen. And you can see that each one of the zeros passes through. Here we have -2, 1, 2, 3, 4, and 5. And so this polynomial gives the zeros 5, 4, and -2. Let's look at some other examples. What if we were to write out a polynomial that had imaginary zeros? What would that look like? Well, let's go ahead and try that. So we're given the zeros are 5, 3i, and -3i. We would start out something like this: x minus 5, x minus 3i, and x plus 3i. And instead of multiplying x minus 5 times x minus 3i first, let's multiply these two together, and then we can multiply by x minus 5. Now, I'm going to do this without the shortcut because I want you guys to see why the shortcut works and how it works differently using imaginary numbers. So, x squared plus 3ix minus 3ix minus 9i squared. Now, The 3ix and the minus 3ix cancel out, and the negative 9i squared becomes positive 9, and so the resulting polynomial that has the zeros of 3i and negative 3i is x squared minus 9. Now we can distribute these two terms, these two binomials. X cubed plus 9x minus 5x squared minus 45. And we get x cubed minus 5x squared plus 9x minus 45. Now when we graph this one, it's going to look a little bit different than the other one that we saw. And that's because the zeros are, some of the zeros are going to be imaginary. So you can see that we have the one real zero, 5, and then the curve continues down and does not come back up again. This is a cubic function with one real zero at 5 and then two imaginary zeros. Now remember that imaginary zeros must come in pairs. Every single square root of a negative number has two roots. Or you could look at it the other way. Every single imaginary number, when squared, has another imaginary number that's the negative, or the opposite, that results in the same negative square. So let's see what happens when we're only given two zeros of a polynomial function. We're given 6 and 3 plus 2i. But technically the other zero that becomes a pair with this one that wasn't given would also be 3 minus 2i. Now the reason why I know that 3 plus 2i and 3 minus 2i are imaginary pairs is because of the rules of complex conjugates. Anytime you multiply two complex conjugates together, you're going to get a real number. We looked at this when we were dividing by complex numbers. So the complex conjugate of 3 plus 2i is 3 minus 2i, because when you multiply 3 plus 2i times 3 minus 2i, the result is a real number, 13. Therefore, when you're doing the factoring, when you're writing the factors in order to write the polynomial function, you have to say x minus 3 plus 2i times x minus 3 minus 2i. Now let me show you how we can multiply these two together in order to have a polynomial. First, x squared, then x times negative 3 minus 2i. Then minus x times 3 plus 2i, and then we're going to subtract 3 plus 2i times 3 minus 2i. I already did it out here, 13. X minus 6. X squared minus 3x plus 2i minus 3x minus 2i minus 13. X minus 6, x squared minus 6x, 2i and negative 2i cross out, and we're left with minus 13. Sorry, plus 13, because it's minus minus makes the plus. And so we have that this polynomial that has 3 plus 2i and 3 minus 2i as zeros is the polynomial x squared minus 6x plus 13. Let's multiply x minus 6 times this polynomial. And so we have the polynomial x cubed minus 12x squared plus 49x minus 78 and let's see what the graph of that looks like. Once again, we have that 1, 0, is at 6, and then there's 2 imaginary zeros.